Hello class, welcome to our discussion over section 3.1, taking a look at minimums and maximums that we call extrema on an interval. So in this first section, we basically just go through and talk about what a minimum is and what a maximum is. Now, sometimes there's some tricky things that can happen. If you look at these first three graphs, we've identified on this first graph that we have a minimum here and a maximum here. On the second graph, we've identified that we have a minimum here, but no maximum here. And the reason there's no maximum here is because there's an open circle. All right, and the same thing happens on this one. Even though a circle's closed in here, the actual graph itself is pointing to the open circle. Therefore, there's no minimum. However, there is a maximum because the highest point on the graph is actually that particular dot that's filled in at 2, 5. So let's take a look at the extreme value theorem. It says that if f is continuous on a closed interval AB, then f has both a maximum and a minimum on that interval. All right, so let's take a look at this Roman numeral 2 here, the graph on the right side over here. We have a relative maximum, right? So relative to all the points around it, this is the highest point. And then a relative minimum here at this lower point, since relative to all the other points around it, it is the lowest. Now, a lot of times in class, I'll refer to these as peaks and valleys. So if it has a peak, that's going to be a relative maximum. A valley is going to be a relative minimum. Another term that's often used is, instead of relative extrema, local extrema. All right, so we'll use these words interchangeably, but we'll use our everyday language in terms of peaks and valleys most often. All right, so now we have a very formal definition of the relative extrema. Let f be a function whose second derivative exists on an open interval. If there's an open interval containing c for which f of c is a maximum, then we call f of c a relative max of f, and so forth and so on. Let's look at an example. All right, example 1a. It says to define the value of the derivative at each of the relative extrema shown for each graph. Now, this first one, example A, I want to find that value of the derivative by inspection. All right, so we have this point here at 3, 2, right? And the derivative we know is the slope of the tangent line. So I'm going to draw my tangent line in at this point, all right? And I'm able to observe by inspection that the slope of this line is equal to 0. Therefore, we can deduce that f prime of 3 equals 0. All right, so just to verify this, I'm going to take this function f of x, and I'm going to look at it on the inspire and find out what the derivative at the point 3 is. All right, so our function 9 times x squared minus 3 over x cubed. All right, so we go to our calculator. We can do menu, and then for calculus, and number 2, the derivative at a point. The variable is going to be x, and the point is going to be 3. Right now we got to put our function that we're taking the derivative of, right? And I believe that was 9 times x squared minus 3 over x cubed. All right, and enter. So we can see here that our slope of our function 9 times x squared minus 3 over x cubed at the moment x equals 3 is 0. So our visual inspection was correct. If we look at part B, it's telling us we have a relative minimum at 0, 0. This is the most basic absolute value function. And we know that that's going to be the lowest point on the entire graph. So let's take a look at the derivative at this point. Well, there happens to be a sharp turn. So since there's a sharp turn, we know that the derivative is undefined. Right? So for part A, the derivative was 0. Part B, the derivative was undefined. All right, part C, again, we're going to use our inspection method. It's telling us we have a relative maximum at 3 pi over 2 negative 1. Excuse me, a relative minimum at 3 pi over 2 negative 1. If I draw in my tangent, the slope at that point is equal to 0. And a relative maximum at pi over 2 comma 1. Again, we draw in our tangent line, and the slope of that tangent line is 0 also. So these values that we were looking at on this previous page, where we had this maximum here, this maximum here, this minimum here, and these two relative extreme here, we notice that the derivative is either 0 or undefined. So that leads us to what we call the critical numbers. Right? And the critical numbers are where the first derivative of a function is equal to 0 or undefined. So whenever we want to find critical numbers, to find critical numbers, set f prime of x equal to 0 or undefined. All right, so this first example here, we have a sharp turn. All right, and at this moment that we have a sharp turn where the x value is equal to c, we have a critical number. Again, on this one, we have a horizontal tangent line, so the slope is equal to 0, and wherever the slope equals 0, we have a critical number. All right, and the reason we need to know critical numbers is because of this here. Relative extrema only occur at critical numbers. So if we want to identify the relative extrema of a problem, we're going to need to first identify the critical numbers and then run some tests on those critical numbers. And here in the next box, you'll see some guidelines. Find the critical numbers of f. That's where f prime of x equals 0 or undefined. Evaluate f at each critical point, so plug in the critical numbers to the original f of x function. All right, evaluate f at each endpoint, so plug in each endpoint into the original function. All right, and then finally, the least of these values is the minimum, the greatest is the maximum. So let's try an example. All right, example 2, finding the absolute extrema on a closed interval. So first thing we need to do is find f prime of x. So the derivative is 12x cubed minus 12x squared. We need to set this equal to 0, undefined, but since this is a cubic function, it's never undefined. So we're only going to be looking for where it's equal to 0 at. So factor out our greatest common factor, right? And then set each of the factors equal to 0 and solve. 12x squared only equals 0 if x equals 0, and x minus 1 only equals 0 if x equals 1. So these are critical numbers. So we found the critical number, step 1. Step 2, evaluate each critical number for f, and then evaluate f at each critical number, and then number 3, evaluate f at each endpoint. So I'm going to start with the endpoint of -1. I like to go in chronological order, and then I'm going to go to my critical number 0 here, and then my critical number of 1 here, and then my right endpoint, which is 2. And we're going to plug back into the original function. So 3 times -1 to the 4th minus 4 times -1 cubed, and that's going to be 3 plus 4 equals 7. Right? Plug in 0, we're going to get 0 minus 0 is 0. All right, plug in 1, you're going to get let's see, a 3 minus a 4. It's going to be a -1. And then plug in 2, it's going to be 3 times 2 to the 4th minus 4 times 2 to the 3rd. All right, this is going to be 48. 4 times 2 cubed is 32, and that's going to give me 16. All right, therefore, our minimum is our lowest number out of these, the outputs. So our minimum is -1, and that happens at x equals 1. And our maximum is our highest value over here, which happens to be 16, and that happens at x equals 2. All right, so now we're going to use the calculator to verify this. So I'm going to bring up my Inspire and put 3x to the 4th minus 4x cubed in it. All right, so we got our graph here, and then we're going to type in 3x raised to the 4th minus 4x raised to the 3rd. Right, and graph it, and we see exactly what the graph looks like over here. And what I'm going to do is I'm going to change my window a little bit. So if I go to menu, I can go to number 4. Right, and I'm going to go to Windows Settings, and I'm going to change my window to be from -1. Oops, let me go change that again. Right, so we're going to go from -1 to +3, +2, our interval that we're looking at. Right, I'm going to scale by 1s. And then my y min and y max, I'm going to go from, let's say, -2 to 10. Right, and again, I'm going to scale by 1. Right, so I can see this graph a little bit better. So we have this right endpoint over here, which is has a y value of 7, and we had a critical number at 0, and we had a horizontal tangent line here. All right, that gave us a y value of 0, and then we had a looks like to be a valley over here, right, and it's the lowest point on the entire graph at -1, and then the right side of the graph, we can't quite see it up here, but it's going to happen at +2, 16. We could also, if you hit Control T, that'll bring up your table. Right? And if we want to put in our own values to that table, of course we can see, we can scroll and we can see -1, 0, 1, and 2. But a lot of times we want to enter our own information. So if you hit Menu and you go to tables, we can edit table settings, and then independent, we can change it to ask. So it'll ask us what we want to type in. So let's say our left endpoint was -1, and that gave me an output of 7. We had a critical number of 0. We had another critical number of 1, and then we had a right endpoint of 2. And you can see that this table looks like the table I've set up here, and got the same minimum and maximum as I did earlier. Okay. All right, let's take a look at letter B. First thing we need to do is to take the derivative. Right, so we have f prime of x equals 2 minus 2x to the -1/3, which is 2 minus 2 over the cube root of x. Now, this is very, very important when you're finding critical numbers. The critical numbers come from where the first derivative is 0 or undefined. So right here, I can tell that it's going to be undefined when x is 0, because that's going to be 2 over 0, and 0 in the denominator is not allowed. One of the things I always do here is when I have fractions involved in my first derivative, I combine to a single fraction. So if I crisscross straight across, I'm going to get 2 on the cube root of x minus 2 over the cube root of x. So now I can see that I'm going to set the top equal to 0 for where my first derivative equals 0, or horizontal tangents. And then I'm going to set the bottom equal to 0 to find those vertical tangent lines, or where the first derivative is undefined. So if I have 2 on the cube root of x minus 2 equals 0, solve this, and we're going to get 2 on the cube root of x equals 2, therefore x equals 1. And then set the bottom equals 0, the cube root of x equals 0, only if x equals 0. So these are my critical numbers. X equals 1 and x equals 0. So now when I need to compare those critical numbers with my endpoints by plugging everything back into the original function. So I'm going to start my left endpoint's -1. Then I have a critical number of 0, and I have a critical number of 1, and I have a a right endpoint of 3. All right, so go ahead and plug those back into your original function, and you should get that the y value is -5 when the input's -1, and when your input is 0, your output is 0. Remember, I'm plugging into the original function here. All right, plug in 1, you should get -1, and plug in 3, and you should get, let's see, 2 times 3 minus 3 on the cube root of 3 squared. All right, so this is 6 minus 3 on the cube root of 9, I believe. All right, so we're going to put that in the calculator, and I believe you should get -0.240.